that is this formula. When ask our question, you just use this formula depend on K1 or K2, right? Which range? And here, some say, okay, I don't think this is a wave propagated to the whole space. It's just a decay very quick. Yeah, this kind of a damping wave, if we consider this classical vibration. But it is just give us the probability to find the particle far away go to the positive infinite is 0. And there is a certain small range close to the boundary is non-zero. That is only the information give us. Okay, so that is the C. Then for E, the probability here, we still go back to see the chapter 3. We introduce the probability definition positive 4. For the discrete spectrum, that means if it, so this one is the operator eigenvector or operator A, for example. Then we solve this, okay, the eigenstates. So the question asks, what is the probability of any state psi of the particle or the system within which is project to this eigenstates? So we just define that project to this one and do the square root, I mean the absolute square, and normalize. So that is first discrete. For the continuous spectrum, if A is a continuous operator, which is eigenvector of operator A, which is continuous, then here, similar like this. So this means we are going to find what is the probability such that the state is in this eigenstate A. Okay, that is A is any eigenvalue which is continuous. Then we do the similar here, but the formula in textbook is a PA over DA. But this just gives us the probability density. That means since this is continuous, so we can say that is continuous density. Then here, A in our case is X, right? So in this case, the question asks us, what is the probability to find the particle of position here? So what does mean? This A in this problem is position operator and position eigenstate, which is X cat, right? So what we do is you just project your states to the X. For given X, we have given states, right? So when X equal to this value, exactly is projected here and normalize. If X equal to 0, so that's just project 0. So these two values actually is now, since when the any function project to X in the position representation function, is this, right? So that is psi X, absolute value take square and normalize here. Then this one, just you use this function here, set to X. Okay, the value, not integral. If integral means the range from position 0.1 to 0.2, then you take integral. But just ask this position, you just substitute the number in this case. So now,
since the kinetic energy was less than the barrier, that's why it's the damping wave?
Yes.
And it's real, not imaginary.
Yeah, that is, yes. So now, in this case, here, the top one is psi, actually it's in the X positive range, right? So that you are going to use psi 2. And the denominator is also 2. You may also say, okay, this boundary is be 2 and 1. Yes, because this be equal, so you can either use 2 over 1. This be equal, right? At this position. You can use this function here when x equal to 0, or this one when x equal to 0, since they are continuous. That makes sense, Pam? Okay. So then, so what you need to do is just, right, just substitute these numbers.
So we didn't have to consider an actual band. We just had to consider the probability density.
Yes.
The thing that caught me off was
I think that is the probably make you confused.
The homework said near those points, so I assumed that meant you had to consider.
Yeah, near you just give a small epsilon in around there. Yeah. So, yeah, sometimes this sentence is not clear, but if you really use integral, you can use, as you say, you did, right? Something like if this a minus epsilon, a plus epsilon, and you do this square and integral here, right? I think this one is 0 epsilon, but you use psi 2. This one is, if you use this one, you should be this one psi 1, this one psi 2, you separate, right? You do that way. Yes, and then you take this, yeah, I think you can use this one here. That is in case if consider it not, I will not say equal, right? Because in case ask in the small range between among this one. But it's not equal to 1. I'm not sure I found either you and someone get equal to almost close to 1. I'm not sure how you get it.
Well, I got it close to 1 because at the border, not only are the functions the same, but their derivatives are the same at the border. And assuming a continuous second derivative, then the integral would be very, very similar at the extended epsilon because of the exact same derivative around that time. And so it's about equal to 1, not exactly equal to 1, but about equal to 1, assuming that the second derivative is continuous.
I got close to 1 because I made a mistake with the imaginary number.
Oh,
so
okay.
then it canceled out. And I was
okay,
like,
that
one,
you use the imaginary here, your concern, I need to consider, you consider the continuum of the second order derivative. So the second order derivatives, they are same? I don't think they are same, right?
The second order derivatives aren't the same, but over the
K1
band,
and K2, they are not same. If, okay, if you use K1, whatever, yeah, let's keep in mind. I just want to know where you get this one.
Well, the reason why I got the, I said it was about equal to 1 is because when
the
we're
derivative
dealing,
the same?
when we're, the derivative is the same, and we're
But
dealing with a
position.
different, different position, but the different position on the order of 10 to the negative 10
Okay,
meters.
you just ask, but actually if you
Which
use
then-
this one, you see that this is not equal to 1. It's very small.
Yeah. And then because if we're assuming epsilon even among the range of 10 to the 10 meters, then the epsilon must be even smaller than that. So there's less of a chance for the second derivative to cause a major issue, which means it's about 1.
I try to think about how to answer your question is derivative, but if we have this kind of question, I just try to use this formula. Okay. All right. Today we continue to discuss the potential well. We almost finished, and we are going to discuss the energy allowed, right? Then we discuss another potential called the delta potential. These two types before we discuss the harmonic oscillator. Okay. So potential. Let's keep continue. Finite square real potential. And we just consider boundary condition right here. Bounded states, because the bounded state, we already discussed how this transmission, right? So now what we consider is here. Symmetric, and this potential, and this is a V naught here, and energy is here, less than V naught. So we have A minus A, right? This is a system we discussed, we didn't finish. Now, we already have the solution for this wave function, so now let me just give this solution, and we're going to discuss the boundary condition. We also finish the boundary condition, so we just need to apply it and do the discussion. So let me first give this, okay, we have the wave function since a parity, right? Because potential symmetric. So we have two types of wave function. Symmetric function is A exponential of K1 x and B cosine K2 x B minus k1x, x smaller than negative half k. That is symmetric and anti-symmetric. We have also used this coefficient. We use the same, but we are going to define this coefficient by the boundary condition. That's we already discussed. So, k2x minus k1x. Okay, that is we have, and then we have the boundary condition by apply this continuum of wave function as and also the this first digit, right? So from the boundary conditions, just give the final result. We have okay. For let's say for the symmetric, we have A equal to B, and for the anti-symmetric, we have A equal to minus B. Right? So that is because symmetric is satisfied. Then we have another boundary condition is this one, and we have another one is k1 equal to k2 tangent k2 half a. Then for the anti-symmetric, we have k1 equal to minus k2 cotangent k2. Okay, I think that is a read we reached to here. Now we are going to discuss from this boundary condition, how can we obtain the allowed energy? Okay. Here, this is clear, right? Because this we are going to have a symmetric, anti-symmetric, so this coefficient is fine. Now, these two equations. These two equations gave us this, because we know, okay, we can take the K1. K1 is K1 is 2m over h bar. K2 is this is I think that is V naught minus let's define the beginning. Yes. Huh? Oh, K2. This is a K2. Okay, no, that's a K1. Right, that's K1. K1 is 2m V naught minus E h bar. K2 is 2m E over h bar. Okay, now we are going to, because these equations give us a lot of energy set up this, right? So now to solve this one, let's define some two parameters I think we also discussed such that we can solve this graphically. So we define alpha is K2 over 2. And from here, since K2 is this one, right? So that gives us energy. E is 4 h bar squared alpha squared over 4ma squared, which is a function of alpha. So we're going to solve alpha. If we find alpha, we can find energy. Second one, we introduce R, which is A over h bar, 2mv naught. Okay. So that means R is a function of V naught. That means depending on how high it is, then we'll have this constant. So you will see with this constant, we have, depend on that, we will have the allowed value is different. So, okay, now when we define this, then we are going to substitute here. This is alpha, right? This alpha, K2, alpha, and then K1 is, let me see, K1, okay. So from there, so we can find K1 is this one. Then we substitute V naught to here, substitute energy to here, so we have K1, I think so we already discussed before, so I'm going to use this. Okay. How to find K1 from this? You can find V naught as function R and put here. This, put in here. So finally you will find this. So I think, okay, so now we're going to discuss. So once we have this, so these two equations, 1, 2. So 1 will go to half of, this is K2, right? And, sorry, K1. This one, right, equal to tangent K alpha, right? That is, we have K2 here also. So K2 is, so we have 2 over A alpha and tangent alpha. Then this one cancelled, so we have equal to alpha tangent. Now I'm going to use 1 prime. New equation. So we are going to solve alpha by satisfy this equation. This is nothing but transcendental equation. Second one, so number 2, is this one. K1 equal to negative K2 cotangent, right? So similarly, K1 2 over A square minus alpha square equal to negative. K2, which is 2 over A alpha cotangent alpha. Again, we have this cancel, so we have R square minus alpha square square root equal to negative alpha cotangent 2 prime. So we are going to solve these two transcendental equations. Either numerically, if you can write program, you just input alpha from 0 to any continue with a small increase, then you can find the solution such as satisfy this or this. Or now we are going to use graph. Graphically, we can also find analytically, not quantitatively but qualitatively, to get this allowed energy, and we can discuss the property of this. So those are equations. So we are going to use the graph frequently. So how to do that? Because the left-hand side is a function, right-hand side another function. So we are going to plot these two functions in the figure graph and then find the cross or the intersect. That is equal, right? So now how to do that? As a function of alpha, right? So alpha we define, you see here, alpha defines K2, which is always positive. So the range for alpha is from 0 to positive, right? To infinity. So now let's plot alpha. Okay. Then here half pi, since tangent or cotangent or a function of internal this, right? So now okay, let's first look the alpha, tangent alpha. Tangent alpha from 0 to go to the infinity when the alpha go to half. Then alpha multiply tangent alpha, same thing, same property, right? So let's be like this. It's alpha tangent alpha, right? And again here also, right? Because from half pi to pi is negative. So we will not consider negative, right? So we consider here. Again, this is alpha tangent alpha. Then here, cotangent alpha is negative, but we have a negative here. So that means from pi, half pi to pi, it is cotangent alpha, negative alpha cotangent alpha, minus alpha cotangent alpha, and similarly here, minus alpha. That is a left sign function. It's two, right? We have two equations. Then we are going to see the right-hand side. Now I'm going to use the color. So what is the function of right-hand side? I'm going to say this is a beta. And this function, beta square equal alpha square, r square minus alpha square. So that means beta square plus alpha square equal to r square. This is a constant, right? So this is a circle. So if this is a circle, then that function means depend on r, how big the radius is, right? Is r bigger than a bigger circle? Is smaller smaller circle? So now let's just consider there's a smaller one and bigger one. Increase bigger. So how to increase bigger? We know this r is function potential V naught. So if V naught here increase, the r increase. That means that the radius, the circle, the radius increase, right? So this line is correspond to different potential state, right? That is V naught. So here that is let's see the beta. That is alpha. So this is r square minus alpha square. So now you can see these two functions be equal, and if equal means on the graph, that is intersect the point here. This particular one I'm going to give alpha 1. That is solution, right? If this one, so we have how many solutions here? We have, and then we discard this one, and then we go to increase, right? So now we are going to discuss. First, if the r is within the 0.5 pi, for the potential V naught, which is within this range, then what happens? Only one intersection, right? So there's only one solution from that. And this solution is from first one prime. Because cotangent, there's no, this curve no intersect with others, right? Only between this, so only this one. And this one prime is from where? From symmetric function. So that is, or symmetric or even function, right? So, or even function, that bounded from here. Okay, so from here, then when we have this R1, so R1, we have, that means R1 is here, right? If there's energy here. So from this R1, we can have this energy E1 is 2h bar square R1 square is for the 2. Yes. It's a 4, the denominator is 2, right? So that's 2. And a square. Okay. So that is in this case, but alpha 1 is between 0 and 2 pi. So that means this E1, if alpha 1 is smaller, right? So that is is the E1, this value is function of R1, and R1 is from 0 to half pi. So that gives us a range of the E1 is always in the range of when alpha 1 equal to half pi. So that is, this one is half pi, is 4 pi squared. And here we have a factor 2. So 4 pi squared is, let me just keep this square, I keep this one and 2 and transfer over and k squared. Here, I just replace alpha 1. If alpha 1 is take this max value, half pi. So that energy in this case, if we have a given potential step here is given, and which is within the value between here, then we will have only one state, this B corresponds to symmetric, and only one allowed energy, this ground state. There's no any other solution. So that means the system, let's just see how big it is, and there's only one possible quantum state or bounded state. And okay, and the function you can also see it is symmetric. So this like the sine x not something like this. It's symmetric, right? So that is the discussion for the small potential finite potential well. Now, if they increase, now they consider second case. Second case, if this R is between pi and half pi. As I said here, R is if you in this case, then we will see here. Color again. So here I have one. Since this increase, right? So I have a 1 here. I'm going to say, in this case, alpha 1, but I have another case, alpha 2. So I have two solutions. One is again the alpha tangent alpha is corresponds to symmetric function. This one is unsymmetric R function, right? So we have a two solution. Two solutions. Here, this alpha 1, alpha 2. This alpha 1 is not this one, right? So, because it's a potential difference. So, depending on the potential step or how high the potential will, then we'll have either only this one or this one, right? So, and then we are going to increase. So, in this case, and you can see here, we have alpha 1, again, it's from symmetric, right? So, I'm going to see. That gives E1. Again, we have this one is the same thing. But this gives the range of this, again, this range of E1 depends on R1. But alpha 1 still from 0 to half. So that E1 is still in this range. So this is symmetric. And this energy is lower since alpha small. If you look here, the energy is proportional to alpha, right? So alpha small, energy small. And that means energy lower, and alpha increase, energy increase. So this be ground state. Right? Then for alpha 2, we have E2 another energy, which is higher than E1, right? And for E2, you will see here, that is within the alpha from half pi to pi. So that is first, or we only have one, so we should say first or just steady state. And in this case, we have two-way function. That is for the anisymmetry. So we have two-way functions. In this case, the symmetric is ground state. Still have something like this, asymmetric. And we have another one is odd or even, or the anisymmetric is, okay, suppose this is energy here, right? So that is a function like this. Similarly, we can consider for the case of for this case, if this R is larger than pi, smaller than 3r, then we have a 3 alpha 1, alpha 2, and alpha 3. We have 3 solutions, right? Here in this case, this one, alpha 1, yeah, this one, alpha 2, and this one, alpha 3. And you can see this symmetric also alternated. First one, this one, energy lowest with a symmetric or even function. Then the second one here, energy highest is first accepted, which is odd function or anisymmetric. And third one, again, go back to the symmetric. So this is alternated. I think then you just go to E1. I will not write it because this formula is similar. And then here you will see E1 is lower than E2. E2 is lower than E3. You have this. Okay. I said this one since you can do similar like this, and you can also discount the function to do it. Now let's consider if R go to infinite. R go to infinite is go to infinite. So what does mean? The potential go to infinite, that like infinite potential, square potential wave, right, which we discussed. When you have an infinite, the wave function at two boundaries is 0. And all the solution we have this energies n h bar square, n square, and pi square over 2ma square. And let's see whether it is true, right, in this case. So that means this is like this case is, okay. So we will have how many alpha n? Alpha n for this, okay, for symmetric, we will have, if this is close to 2m plus 1 pi, you can see here. From here to here, you already see this, so with increased r, the alpha 1 is close to the half pi, right? So when we increase r, go to infinity, you can imagine that it's a big circle, and the cross or intersection is close for this first range from a to 0 to half pi is almost here, right? And then for next one, tangent alpha tangent alpha, another is close to 3 half pi, and all the odd number, 2n plus 1, so n from 0, 1. That is the odd number, right? All the odd number will have this intersections. We have a solution for this. And we have another group is for the anisymmetric function is here. From half pi to pi, when you see when we close, you see this alpha 2 there. So this big alpha 2 is close to pi. If you increase alpha, you see very close to pi, right? So pi is 2n or 2 pi, right? Or even n from 1 to. So we combine together, these two, we are going to use alpha n as n pi over a. Okay, now n from 1 to you can see here, when n equal 1 is here, when n equal to 0 case, right? Half pi. Is this one. Then when n equal to 2 is this one, when n equal to 1. Then the n equals 3 is this, when n equal to 1, right? So you can see we combine together, actually it follows the same formula, then n from 1 to 3. All the integer number not from 0, since there's no 0, only from 0 to pi, right? So this is the smallest, this one. Okay, then how about energy? Energy is here, right? So alpha has an integer number, discrete numbers. When the energy corresponds to that one, we will have also index n. And you will see that is very easily. You just substitute this alpha n to here, you compute. And here, this is an infinite square potential wave, right? And yes, that makes sense. We know we solve the infinite when the R goes to infinite means this the energy this step is go infinite higher and that close the infinite square wave. And yes, the solution also close. Go to that limit. So this is example how we deal with the finite potential wheel, which and then we discuss when go to the infinite, it is go to the infinite potential wave. But the difficulty is that if the finite will have solved the transcendental equation. But if infinite, it is very easy we already solve. Right? That is first, and then we go to this one. Now I'm going to discuss another type of the potential which has similar transcendental equation and how to solve this. So give you more idea or familiar with this type of the problem or potential. Can I use this part? Okay. Before we discuss the totally different potential, which is harmonic oscillator, so now I want to discuss another one, which is the problem 4.5, so in the textbook. 4.5. And so this potential is the Vx is delta function. And first give the formula. Symmetric. And x equal to a and x equal to minus a. So that is potential looks like here. Since we use minus, right? If this is minus a, this a. Vx only when x close to a or minus a will give us this infinite, right? Otherwise it's 0. So that is like this. Here, say that is V naught, and minus negative V naught, right? So that is the behavior of this potential. Okay, so now let's solve this type of the potential. What kind of wave function, the solution from the Schrödinger equation, and what is allowed energy. This type of potential is practically, it's pretty much like we have a metal, and this surface is air, right? So you see the metal, the electron, if a conductor is free, almost like free part. Then when you come to here, so that this is a surface or boundary, right? Then you see the potential suddenly change. So to mimic that one, we use delta function since the change is at this surface. Or if we have a two conductor, conductor 1 and conductor 2, here is the interface, right? Then the particle or the electron from here, from 1 to 2, this interface, a kind of energy barrier. you have to overcome this energy barrier, and not something like this. I mean, you have a positive energy barrier, right? This is negative, it's like an energy well. So practically, it is, we can use this delta function potential to mimic this kind of phenomenon. Then we are going to discuss what kind of solution, right? So the first term is in the potential equation, let's write down first term independent. Okay, kinetic energy, we know this. Potential energy, right, that one, so we have to just write down here. V naught inside delta x minus a plus delta function x plus a sin x equal to e sin x, right? That is the Schrodinger equation. Or we make this denominator this factor, so we want to make this the coefficient for the second order derivative is 1. So, or we just write. Then this negative became plus, right? Plus 2m v naught or h bar square. Here, just divide it. And inside still delta function. So x. And here we have a negative 2me over h bar. I moved to the left hand side, so this is plus. 2me over h bar squared. Okay, we are interested in the bounded state, so interesting focus, let's say, focus on, let's just say, focus on the energy symmetric bounded state, or bound state. You can discuss the unbounded, but that is like transmission, right? So just you transmit, and here there's some influence, and we keep going. But we will consider here. If energy is lower or negative, what kind of solution, right? We consider this. Okay. Now to solve this one, let's consider this potential. This potential only non-zero or go to infinite when at these two positions. Otherwise, all are zero, right? So let's solve the solution with exclude these 2 points. So let's for x not equal to plus minus a. Let's see the solution. Then we are going to consider this, right? So for this case, the Schrodinger equation became this term is 0, right? So only this plus 2 and or x plus 1. What kind of solution? It's a sinusoidal function or exponential.
Sinusoidal.
It's negative. So here is negative, right? Yes. So it is exponential. Or minus k squared, I'm going to say equal to 0. Here I define k is 2m. I'm going to use absolute value of energy. So just be careful what we discuss, the energy, which is positive or negative. Okay. So then the solution general, right? So now this is in general. Mathematically, we have the formula like this, right? It's A, E, kx, and another is negative kx for x in this range, right? Not equal, since equal, we have another potential. Is this. But physically acceptable solution we need is finite, right? So now, if we need finite, we have, okay, here before that, before this, this since the symmetry, otherwise there are different types. So now let's see here, and then there is the symmetry analysis. Here, the potential symmetric, right? Because the potential symmetric, so we know this Hamiltonian commute with parity operator. That's the same as we discussed for the finite potential wave, we have also symmetric, right? So what that means, the wave functions have parity, right? Mass has well-defined parity. So now we have two, symmetric, or symmetric, and anti-symmetric, two types. Then now we are going to consider the physical. Here we are going to physically acceptable for symmetric and anti-symmetric. Okay, for symmetric, when x negative, here, when x negative, this one decay, since from the minus a to the minus infinity, this one, okay, but this one diverge, right? So we cannot take this one. So the a exponential kx for x less than minus 8. Then between minus 8 and a is finite, so any solution is possible, so that the linear combination of these two should be okay. Then we can write this linear combination is similar as hyperbolic cosine kx, right? Again, I didn't use equal here. Of course, we need set equal if these functions be continuous, right? So now let's see. And then this symmetric for x larger than a is we take this one, not this one, since this diverge, right? So that is, and then even symmetric, this coefficients we say, we just need to know that. So and it's a minus kx. So that is the first symmetrical even function. Then similarly, we can also get this anti-symmetric for R function. We set A since the anti-symmetric, when x equal to minus equal to the minus x equal to the negative of positive x, right? So we are going to set up negative, and again we are going to take the finite. Then the intermediate still same thing, but we need this one has a symmetric, right? So we use a hyperbolic cosine. But anti-symmetrics be hyperbolic sine. And then this positive, we have the same anti-symmetric, so here, e minus kx, right? Okay, and the behavior like this. So you can see this is a minus a. Is a if it's symmetric as a function of x. That is the like this. And this one, this negative a is this dominated by this, right? And this positive a is dominated by this exponential. And between minus a and a, followed by the hyperbolic cosine. Similarly for this one, it's anti-symmetric a minus a. So anti-symmetric here. That is only symmetry. Okay, wave function we solved. Now we are going to solve this allowed eigenvalue, right? So the solution here, now allowed energy. How to do that? We are going to use boundary condition, right? Always boundary condition. Boundary condition first, the continue wave function will continue at minus a and plus a, and it's a derivative. So let's first consider the wave function that continue at this boundary. What is simple? This is the continue. It is continue, right? If we plot here, it is continue here. It is continue here. So for this one, at x equal to a, we have a is this positive, right? So this two part. A exponential minus ka is equal to b hyperbolic cosine ka, right? These two. Then another is x equal to minus a, and this one. Same thing. There's x equal to minus a is a minus, and here cosine minus ka is be positive, because cosine hyperbolic equal to a negative x has to be positive, right? So that is again same thing. So you see these two boundary condition gives us the same formula. And it's same thing. So that is for the continue of the function. Let's look at this anti-symmetric similar at x equal to a. Now is this two, right? So that is a exponential minus ka equal to b hyperbolic sine ka. For x equal to minus a, so we have a negative a exponential minus ka. That's it. Okay, equal to b sine, hyperbolic sine minus alpha equal to minus hyperbolic sine, right? So minus b sine hyperbolic ka. Then you can see minus minus cancel. So these two equations are the same. These two equations are the same, right? We just take one of them enough. That is the condition. For one of the condition we have applied for the continuity of wave function. Now the next condition is the first derivative. From here, we immediately know this is the disconnect, right? You see this from this side, if we derivative this go to the up, and this so that is a disconnect. Then that is we cannot use this function immediately, but do the derivative. So we need to follow this continuity. We need the continuity of the unity of from the Schrodinger equation. Since we the Schrodinger equation of the derivative, right? They follow that. It must be followed up. So we can use this equation to give us the continuity condition of the first order derivative. How to do that? You remember we just solved the Schrodinger equation, ignore these two, right? Now we are going to include. So this is around, let's consider around x equal 8. First, then we consider the second one, right? In this case, the potential is, sorry. Only this part, right? So around here, the potential is only this part. this part is not considered because we only consider around here, right? So this differential equation here. Okay. Plus 2m naught plus square and delta x minus a sin x equal to plus 2m e over h plus square sin x equal to 0, right? That is the function. But from here, this is a go to infinite when x close equal to a or close to a. So to solve this one, we are going to, it is better to take the integral, and by this, just consider around a, so we take the integral but take the epsilon is go to 0. So now what we have to say is this one, a minus epsilon to a plus epsilon. When epsilon go to 0, that is around a, right? That is this formula. So they are equivalent. Then now here, okay, then we have just right. This inside is this track. So we are going to deal with this. If this is integral equal to 0, we do the integral between the thing very small, near the a, that's also equal to 0. So now let's look at the third term. 2m e is a constant, right? Outside, and from a minus epsilon, a plus epsilon sin x dx. Let's look this term. So when epsilon go to 0, almost you can see here. Now please, let's keep constant. This is not big deal. So now here, this one is equal to then and multiply the area, right? The area dx is from a plus epsilon minus a minus epsilon. And this one is 2 epsilon. So when you see here, this is our constant, this is a psi, because there's a continuum. So that is function when x equal to a, but we have this term, epsilon, when x equal to 0, this term no contribution, right? Okay, because this, so now this equation is reduced to the two terms. Only this one, okay, a minus epsilon, a plus epsilon, and inside this one, I'm going to say that is d, so the first order derivative, dx, dx. Now this is, this one is equal to this one, right? Okay. Plus this one. A minus epsilon, a plus epsilon, 2m a naught, a plus delta function, so you know how to solve delta function. That's equal to 0, right? Because third term, this term is contribution 0, so only these two. Then you can see here, this first term, it is equal to this integral is totally differential, right? So that is d psi x dx when the first one is a plus epsilon and minus the value here, dx, a minus epsilon, right? This first term. Okay. Now, so in this case, this one, since it's a delta function and this a just within this range, right? So that is 2m a naught h plus square. Then the function itself, right, equal to a, right? So that's equal to 0. Then the second term does not depend on epsilon. I can move to the right hand side. So finally, we have this formula is this. Limit epsilon to 0. The first term is the first order derivative of sine x when x equal to a plus epsilon. Subtract the second one, x equal to a minus epsilon. Not equal to, I move this to the left hand side to negative, 2m a naught and plus square second. Or I erase that. Okay. So that is equation, I didn't give a name, right? So now I'm using equation 1. Okay. Now, we are going to use this one to determine the boundary condition. This boundary condition gave us this first order derivative at this a, right? So how the next one is we are going to calculate this one, this one. This function depends on symmetric or antisymmetric. So we solve both one by one. I just erase the function so you know that that is cosine, right? Remember the symmetric is hyperbolic cosine. And you do the derivative, we have a k. This one we have a minus k, right? So this one is this one, and this one is this one, right? That makes sense? Okay, so now let me give just this d sine s x dx when x equal to a plus epsilon is this one. That is minus ka exponential ka, right? And the second one is when x equal to a minus epsilon. Let's do the derivative of this one. Sine, again, sorry, that is antisymmetric. We have a cosine, right? It's symmetric. So cosine do this is we have a negative. We do not have negative. Let's see, k b. Oh, sorry, here. That's be a plus epsilon. That be parabolic sine k a minus epsilon. Yeah, that is no negative sign, right, for the hyperbolic. Okay, so now we have this. Now we are going to substitute these two into here. So we'll have, when epsilon go to 0, then we have two terms. The first one is minus ka exponential k a plus epsilon minus k b hyperbolic sine k a minus epsilon equal to minus 2mv naught and plus square sine a. Sine a here, because we have continued, you can either use this one or this one, but I prefer use this one because this one makes this, they have exponential term, so that's why I'm going to say, since they are equal, right, so you just select this is a x minus ka. Okay, then you can see when epsilon go to 0, this is a k, right? Minus ka. This one is hyperbolic sine ka. This term go to 0. Then you have this term similar with this term, but you have a coefficient different. So I'm going to organize this one. Finally, is I have this formula. Minus 1 exponential minus ka equal to b. Yes, equal to b hyperbolic sine ka. So now this is equation 2. We're going to, that is for this symmetric. For antisymmetric, similar things. Again, this is apply right? What here? You substitute into here, so then we got this, and you get 2. Similar things, d sine ax dx and x equal to a plus epsilon is equal to minus a k exponential minus k a plus epsilon. Then x equal to a minus epsilon is the sine hyperbolic sine become a hyperbolic cosine. A b hyperbolic cosine k a minus epsilon. So apply equation 1. So I just gave you the final result since these are similar things. We have a 2 mv0 h bar square minus y exponential minus ka equal to b hyperbolic cosine ka. Now I'm going to say equation 3. Similarly, for x equal to minus a, we got the same. So I just give you a result. You can do yourself. For this, we got this formula here. We have a to mv not similar, exact same equation equal to the hyperbolic sine ka. And for the anti-symmetry, we have a to mv naught plus 1 minus 1. Sorry, exponential term equal to b hyperbolic sine ka is equal to b hyperbolic cosine ka. So because the same, so then what happened, that means that we only need 2 equations. This one, number 2 and number 3. That's enough for x equal to 8, positive. Okay, now we are going to find this solution. What's the allowed energy from this formula? We are going to, again, okay, summarize the, I need to summarize the way I'm going to do this. We have for the symmetric function, both the function continue and the derivative continue, we have 2 equations. A exponential, I just erase for me, write down again. Ka and a 2 mv naught h plus 1 minus y exponential ka equal to b sine ka. Okay, 4, 5. Then for the anti-symmetry, we have a exponential minus ka equal to b hyperbolic sine ka and a 2 mv naught plus 1 minus 1 equal to b cosine ka. 6, 7. Then we have, let's use 5 divided by 4. You see that this term cancel, right? The coefficient also cancel. So we have very clear the function hyperbolic tangent Ka equal to 2 mv naught plus 2 minus 1. And then from 7 divided by 6. Similar. This divided, you can see here, this is cosine, hyperbolic cosine, right? Tangent, hyperbolic cotangent. So now this is hyperbolic cotangent, Ka equal to 2 mv naught plus 2 minus 1.
for you.
Yes.
Your last line at the far end of the board, your asymmetric, you should still have the exponential in there, right?
Yes, yes, you're right.
Okay.
Yes. Okay, and up to now, this two again is a transcendental function. So, or transcendental equation. Then we are going to solve, let's still solve this graphically. So now, to do that, we are going to introduce some of a new constant or parameter as we did for this finite square wave, right? So define y is, let's see, y is ka. Then from here we have energy, since that is absolute value, which is n plus y squared over 2n squared. So that means it is function of y. When we solve y, we are going to allow energy. Second one, we will introduce gamma, which is 2mv naught over h squared. So that is a function of v naught, like this, the capital R we did before, right? Change this one, then this change, so this value will change. Then when we introduce y and gamma, so this 2 will become a simple tangent, hyperbolic tangent 1, right? This is 1. And equal to gamma over y minus 1. You just substitute v naught into here, you will see that this one. Now I'm going to say equation 10 and hyperbolic cotangent. Right? Cotangent y equal to gamma over y minus 1. So what we need to do is solve these two. And again, to solve these two depends on how big it is. This we know. Let's first discuss. For this case, let's look at this one. Right? So this graphically we can see very easily. This is a 1. Tangent, hyperbolic tangent is, then y go to infinity, go to 1. So that is hyperbolic tangent 1, right? And this one, 1 over y minus 1. So that is something like this. Gamma over y minus 1. And here, you will see here, this is a y equal to gamma. So because y equal to gamma, then you see gamma is 1, right? That gives us gamma over y minus 1 is equal to 0. So that means this decay to here 0. And at equal to 1, then when, okay, let's say like this. When y equal to half gamma, then you will see here gamma over y minus 1 is equal to 1. That's here. So that is half gamma. Then where's the intersection here is here, right? So assume that is solution is again y naught. Then we know the solution y naught is smaller than gamma and larger than half gamma. Then you have the energy, right? E naught corresponds to y naught. Absolute value is h bar square y naught square over 2 square. Not only one, no any states, right? So the only one. Only one bound state. And this state is symmetric. No antisymmetric. Why later? I do not have time. Because this one is cotangent, hyperbolic cotangent, you will see there's no cross term. Okay, now we can continue and finish this discussion on Wednesday. Then we go to the harmonic oscillator. Both or just this quantum, right? Okay, and then the tomorrow. Okay.
Time to go decorate.
Yeah.
Go make that.
going to make a stop on the way over there, but
Cool.
I will meet you there.
See you soon.
See ya. Bye, guys.
Oh, okay, all right.
Yeah, I'm gonna stretch myself and then break.
I think like the last thing I need is a new project, and I keep picking up new projects.
I can't say no.
It's like, oh, there's a thing, let's go do it. Like I've agreed to try and help out, like, the process of reopening the planetarium and stuff. It's like, I don't need more to do.
I was in a fraternity in my undergrad, and there was a time where we needed to put on like a really big party or something. I forgot what the situation was. They're like, we need this party to go on well, we need this party to be like be super good, we need everyone to love this party. Ty don't go.
Oh.
They literally were like, we need every brother there except for Tom and Michael. Because I just don't do well at parties, and they're like, you're kind of cringe every time you go to one, brother. You're kind of cringe.
They're like, this is a social thing, but don't come to the social thing. Like,
Yeah. I mean, they were right. I was quite cringe.
I mean, for real, I'd be like, oh, thank God I'm off the hook.
Exactly how I was.
That's a lot to take in.
today Halloween?
Yeah.
Today?
Yeah.
It's 2 days ago. Because I saw everyone. They were custom.
Yeah. Oh, it's just another day for me.
Really?